Hello everyone, welcome to our mathematics. So today we are going to solve a very easy equation that seems like an easy one, but you can never say because you should never judge a book by its cover. So why I'm saying this? Let's look into the equation and you will find the answer. What we are given? We are given that x plus 1 whole to the power 3 is equal to 1. Let's solve this equation. What we are given? We are given x plus 1 whole to the power 3 is equal to 1. When we solve this, what we get? We get x plus 1 whole to the power 3 whole to the power 1 by 3 is equal to 1 to the power 1 by 3. This means x plus 1 whole to the power 3 into 1 by 3 is equal to 1 to the power 1 by 3. This gives us x plus 1 whole to the power 1 is equal to 1 to the power 1 by 3. This means x plus 1 is equal to 1 to the power 1 by 3. Now, what is 1 to the power 1 by 3? It is nothing but cube root of unity. And there are 3 cube roots of unity, obviously. What we mean by cube roots of unity? That means we are getting 3 numbers, 3 distinct numbers, A, B and C, belonging to the set of complex number, such that A cube is equal to B cube is equal to C cube is equal to 1. That means we are getting 3 numbers such that their cubes are nothing but 1, that is unity. Now let's find out what is cube root of unity. From de-Moiré's formula we know we can represent, when we represent a number, a complex number in polar form. Suppose there is a complex number, it can be written as r cos theta plus I into sine theta, where r is nothing but modulus of z and theta is the argument of z. Then z to the power n is equal to r to the power n cos of n theta plus I of sine n theta. Here I is iota, that is root over minus 1. Now if we have to find the nth root of unity, what we will get? That is root over n into 1, that is 1 to the power 1 by n is equal to 1 can be written as 1 into cos 0 plus I into sine 0 whole to the power 1 by n, or it can also be written as into cos 2 pi k plus I into sine 2 pi k, where k is equal to 0, 1 and goes on up to n minus 1. It's possible. Then what do we get? We get, seems like cos of 2 pi k by n plus I into sine 2 pi k divided by n. And since k lies between 0 to n minus 1, and obviously n belongs to the set of natural number, what we get about cube root of unity? 1 to the power 1 by 3 is equal to cos of 2 pi k by 3 plus I into sine of 2 pi k by 3, where k is equal to 0, 1, 2, as n minus 1 is equal to 3 minus 1, that is 2. So what we get? Suppose let these as zk, then z naught, or we can say when we replace the value of k as 0, what we get? We get cos 0 plus I of sine 0 is equal to 1 plus I of 0, that is 1. Z of 1 is nothing but cos of 2 pi by 3 plus I into sine of 2 pi by 3, that is minus of, you know what is cos of 2 pi by 3? It's nothing but minus of cos pi by 3, and that is, as you all know, nothing but minus half plus I, and sine 2 pi by 3 is root 3 by 2, and similarly z2 is cos of 4 pi by 3 plus I into sine of 4 pi by 3, that is minus half minus I root 3 by 2. And you can see that these three are the cube roots of unity. We denote this as omega and this as omega square. Then cube roots of unity are 1, omega and omega square. Then the equation we are given was x plus 1 whole cube is equal to 1, which implies x plus 1 is equal to cube root of unity. This means x plus 1 is either equal to 1 or x plus 1 is equal to omega, or x plus 1 is equal to omega square, which gives us x is equal to 0 or x is equal to omega minus 1 or x is equal to omega square minus 1. That is, x is equal to 0 or x is equal to minus half plus I root 3 by 2 minus 1, or x is equal to minus half minus I root 3 by 2 minus 1, which gives x is equal to 0 or x is equal to minus 3 by 2 plus I root 3 by 2, or x is equal to minus 3 by 2 minus I root 3 by 2. Therefore, the roots of the given equation, that is x plus 1 whole cube is equal to 1, are 0, minus 3 by 2 plus I root 3 by 2, and minus 3 by 2 minus I root 3 by 2. Thus the given equation has 3 complex roots, and that's why I said that the equation may look simple, but it involves some complexity. So that's all for today, guys. I'll be back with some more very interesting topics, some very interesting questions. Till then, bye bye.